Okay, our lesson today is to be able to look at the perimeters of similar figures and the areas of similar figures and the relationships that exist between them. Okay, our first rule says that when two figures are similar, the ratio of their perimeters is equal to the ratio of their corresponding side lengths. So we have the ratio of perimeter of triangle ABC to the ratio of the perimeter, the ratio of the perimeter of triangle ABC to the perimeter of triangle DEF is equal to the ratio of the corresponding side lengths. So the perimeter of one triangle to the other is equivalent to the ratio of the corresponding side lengths AB to DE, or you could choose BC to EF, or you could choose AC to DF. All right, but let's take a look and see, what that rule means with some real data. So I decided to draw a couple pictures, that we can play around with to see how these rules, really do work. All right. So we have our first picture, right? This is a rectangle that's 2, 4, 6. That's 8 by 4, and we have another rectangle that's 4 by 2. And if I find their perimeters, the perimeter of the first rectangle is going to be 8 plus 4 plus 8 plus 4, so that's going to be 24 for that perimeter. The perimeter of this rectangle is going to be 4 by 2, or 4 plus 2 plus 4 plus 2. It's going to be 12. So we're saying that the ratio of their perimeters, so 24 to 12, is going to be equivalent to the ratio of the corresponding sides. So let's pick the ratio of 8 to 4. All right, is 24 to 12 the same as 8 to 4? Well, 24 divided by 12 is 2. 8 divided by 4 is 2. So it seems like, that rule works here. And because the ratio of the perimeters, 24 to 12, is equivalent to the ratio of the corresponding sides, 8 to 4. What about the other corresponding sides? 4 to 2. Is 4 to 2 the same as 8 to 4? And yes, it certainly is. So it seems like the rule works pretty well for rectangles. Let's try the rule for some triangles. So here's a triangle that's 8 by 2, 4, 6, and the corresponding triangle then would be 4 by 3. Now the perimeters are a little tricky for triangles because we have this diagonal, but hopefully those of you that are watching the video recognize that we have a very special right triangle here. Right, this is our Pythagorean triple triangle, which we recognize as the 3, 4, 5 triangle. Right, so normally we would find that length by using the Pythagorean theorem, a squared plus b squared is c squared, but because it's a right triangle and it's the most recognized right triangle, I know that that segment's going to be 5. And because the figures are similar, I know that this segment here is going to be 10, because that's a 6, 8, 10, which means it's a 3, 4, 5 triangle times 2. So now we can talk about the perimeters. The perimeter here would be 8 plus 6 is 14, plus 10 is 24, and the perimeter here would be 4 plus 3 is 7, plus 5 is 12. So the ratio of their perimeters would be 24 to 12, once again. Is that the same as the ratio of the corresponding sides, 8 to 4? Well, we know that that's true because 24 over 12 is 2. 8 over 4 is 2. But what about the ratio of the corresponding sides here, right? 6 to 3. Is 6 to 3 the same as 8 to 4? And it certainly is. So we want to be able to use that relationship over and over again to solve different problems. Okay? Well, first the problems start off pretty simple, like these. Right? It says find the ratio, red to blue, of the perimeters of these similar rectangles. Red to blue, we have this smaller rectangle to the larger rectangle. And if we find that ratio 4 to 6, right, if we're using the ratio of the corresponding sides, that's going to be equal to the ratio of the perimeters. 4 to 6 simplifies to 2 to 3, so I know that the ratio of the corresponding sides, 4 to 6, would be the same as the ratio of their perimeters, which would be 2 to 3. Okay? And let's take a look and see what that's going to mean here. All right, here we have, let's see, the height of figure A is 9 feet. The height of a similar figure B is 15 feet. What's the ratio of the perimeter of A to the perimeter of B? Well, A to B is 9 to 15. That's the ratio of the corresponding sides. We know that that's going to be equivalent to the ratio of the perimeters. 9 to 15 simplifies to 3 to 5. So I know that the ratio of the perimeters would be 3 to 5. All right, here's our next rule. It says that the areas of similar figures, the area of triangle ABC to triangle DEF is equivalent to the square of the corresponding side lengths. So the square of AB, the ratio of AB to DE. Okay, let's see how that's going to work using some real numbers. So our same rectangles that are 8 by 4 and 4 by 2. Now we're going to take a look at their areas. So the area here is 8 times 4, which is 32. And the area here is 4 times 2, which is 8. And our rule says that the ratio of their areas, so let's see, 32 over 8, right, that simplifies to 4. The ratio of their areas is equivalent to the ratio of the square of the corresponding sides. Well, if we look at the corresponding sides, right, we have 8 to 4, right, but we square that. So 8 to 4, 8 divided by 4 is 2, 2 squared is 4. Right, so it looks like the rule works with those corresponding sides. The ratio of the areas is equivalent to the ratio of the corresponding sides squared. Let's try the other corresponding sides. 4 to 2. Right, is 4 to 2 squared the same as 32 over 8? Of course it is. 4 divided by 2 is 2. 2 squared is 4. So we just want to be able to use that rule, that the ratio of their areas is equivalent to the ratio of the corresponding sides squared. See if that rule works for triangles. Right, so this is 2, 4, 6. This is an 8 by 6 triangle. Right, that's a 4 by 3 triangle. We don't need to know the length of the hypotenuse because we're just looking for the areas. So area is 1/2 base times height. So 8 times 6 is 48. Half of 48 is 24. Here the area would be 4 times 3 is 12. Half of 12 is 6. So we find the ratio of their areas, 24 over 6, right, that's going to be 4. Is that equal to the ratio of the square of the corresponding sides? Well, we know that 8 to 4 squared works because that's the same as the other problem, so we know that that's 4. What about the other corresponding sides, 6 to 3? Well, what's the ratio of 6 to 3 squared? 6 divided by 3 is 2. 2 squared is 4, right? So that rule is going to work for us too. Okay? So let's use that rule, see how it's going to work for us. It says find the ratio of red to blue of the areas of the similar triangles. Well, we're given the corresponding side lengths, right? 6 to 10. And we know that the ratio of their, the ratio of their areas is equal to the square of the ratio of the corresponding sides. So if I square this, 6 times 6 is 36, 10 times 10 is 100, right? And we simplify, that's going to be 18 over 50, which is 9 over 25. 9 over 25 has to represent the ratio of the areas. All right, and let's do the same thing for the next problem. The base of triangle P is 8 meters. The base of a similar triangle Q is 7 meters. What's the ratio of the area of P to the area of Q? Well, once again, we're given the ratio of the corresponding sides, 8 to 7. And we know that the ratio of the area is equal to the ratio of the corresponding sides squared. So we have to square that ratio of 8 to 7. 8 times 8 is 64. 7 squared is 49. 64 over 49 is a fraction in simplest form. So we can leave it just like that. Okay? So let's continue. All right. We want to be able to use proportions to find the perimeters and the areas. Okay? Well, the rectangular pool and the court are similar, right? So we're talking about this rectangular pool here and this tennis court here. So use the ratio of the corresponding side lengths to write in solid proportions to find the perimeter and the area of the pool. All right, so what's that going to look like? Well, first we start with the perimeter of the perimeter of the court, and the perimeter of the court is going to be, let's see. Oh, the perimeter of the court is 60 yards, so we're going to write that as 60 over the perimeter of the pool, which we don't know, so we're going to just use P to represent the perimeter of the pool. But then we need the ratio of the corresponding side lengths. Corresponding side lengths are going to be 10 to 18. So there's our proportion. All right, proportion are two equivalent ratios. We cross multiply. P times 10 is going to be 10P. 60 times 18 is 1080. We want to divide both sides by 10. Right, P is going to be equal to 108. Right, and those are yards. So the perimeter of the pool is going to be 108 yards. Right, let's see how that's going to work if we use the same idea, but the rule for area. The area of the court. Well, the area of the court is given as 200 square yards. So it's going to be 200 in the numerator over the area of the pool. Well, the area of the pool, once again, that's our unknown, so we're going to use the variable P. That's equivalent to the ratio of the width of the court to the width of the pool. Width of the court, right, that's going to be 10 to the width of the pool, that's 18, right, but the square of the corresponding side, so we have to square that. So if we simplify, it's going to be 200 over P is equal to 10 squared is 100, 18 squared is 324. So there's our proportion. We cross multiply. 100 times P is 100P. 324 times 200, that's going to be 648. Put two zeros, that's 64,800. When we divide both sides of that equation by 100, they cancel. P is going to be equal to, what's that, 600, right, 648. Those are going to be square yards, right, and that's going to be the area of the pool, right, so that's going to be the area of the pool. It's going to be 648 square yards. All right, we move on. So those same rules we can reword just a bit. So let's take a look at how we can reword them. If figure B is similar to figure A by a scale factor, then the perimeter of B is equal to the perimeter of A times that scale factor. Right? So it's the same rule, just reworded a bit. That's the rule for area would be worded this way. If figure B is similar to figure A by a scale factor, then the area B is equal to the area of A times the square of the scale factor. Okay? So we'll continue to solve problems, right, using the proportion idea. So let's take a look at this next example. Two rectangles are similar. One has a length of 6 inches and a perimeter of 24 inches. The other has a length of 7 inches. What is the perimeter of this rectangle? Well, I think it helps if we sketch some pictures. So I'm going to sketch two rectangles here, and let's pretend that they're similar. Here the perimeter is 24, and we know the side lengths are 6 and 7. Okay? Well, what proportion can we set up here? Well, I can set up a lot of different proportions, but let's set up the ratio of the corresponding side lengths. If I use 7 to 6, right, and I'm looking for the ratio of the areas, the variable here, n, which is what we don't know, over 24 would be my other ratio. Right, remember the rule. The ratio of the corresponding sides is equivalent to the ratio of the perimeters. All right, we cross multiply and divide. 6 times n is 6n. 7 times 24 is 168. And when we divide both sides by 6, n is going to be equal to 28, and what are those, inches, for the perimeter of the other rectangle. Try another one. Triangle LMN is similar to triangle PQR. Here's LMN, here's PQR. If the perimeter of triangle LMN is 64, right, so the perimeter here is 64, what is the perimeter of triangle PQR? Well, once again, our rule says that the ratio of the corresponding side lengths, well, let's say if I use 24 to 18, that is equivalent to the ratio of the perimeters, right? Well, I have the larger triangle in the numerator here, so the 64, the corresponding perimeter is going to go in the numerator there. In the denominator is going to be the perimeter we don't know. When we cross multiply, 24 times n is 24n. 64 times 18 is going to be 1152. When we divide both sides of that equation by 24, n is going to be equal to, what's that going to be, 48, right? And that is the perimeter, so those are meters. All right. Next problem. In a scale drawing, the perimeter of the garden is 64 inches. Right, so that's the perimeter of the garden in the drawing. The actual length of segment AB is 18 feet. Right, so that's the actual length of the garden. The corresponding segment, we want to know the perimeter of the actual garden. Okay, so let's set up our proportion. We use the ratio of the corresponding side lengths, so that's 24 inches to 18 feet. That is equivalent to the ratio of the perimeters. Well, we have the perimeter of the garden is 64, those are inches, and we're going to be looking for this in feet here. Right, so that's going to be n. When we cross multiply, 24 times n is going to be 24n, and that's going to be equal to, what's that, 1152. And when we divide both sides by 24, divide by 24, they cancel, and it's going to be equal to, that's 48, and that would be meters. All right. Here, I just wanted to go back and see this, right? And this, yeah, this should have been 24. Oh yeah, no, they're both okay. That's good. And all right, so we continue. Next page. The Eddingtons have a 5-foot by 8-foot porch on the front of their house. They're building a similar porch on the back with double the dimensions. That's our scale factor. Scale factor of 2 if we're doubling the dimensions. What, or find the area of the back porch. All right. Well, let's sketch some pictures here. So I have one rectangle that's 5 by 8, right? That is the what they have now, but they're doubling the dimensions. So if we double the dimensions, that's going to be 10 by 16. I know the area here, right? Area here is going to be 40, right? The area here is going to be 160, right? And those are square units. And we want to find the area of the, oops, we don't know the area of the back porch yet. So I know the area of the back porch would be 160 square feet. But we want to use that rule, right? So if I'm using the rule, right, let's pretend we didn't draw the picture here and I'm using my rule. Our rule says that area 2 is equal to area 1 times the square factor, I'll use SF squared. How's that going to look here? Well, let's pretend we didn't have this information here, right? Area 2, which is what we're looking for, is going to be equal to the area 1, which is 40, times the scale factor, right? The scale factor is going to be 2, and then we're going to square it. 2 squared is 4. 4 times 4. Area is going to be 160. Right, and those are square feet. So if I did not draw this little model here, right, I could have done the problem this way using that rule that we had. Now that's going to be real helpful because we can't always draw models. So let's try to use that rule to help us with some of these other problems. Okay? So Malia is painting a mural on her bedroom wall. The image she is reproducing is 4.8 inches by 7.2 inches. If the dimensions of the mural are 10 times the dimensions of the image, right? So there's our scale factor of 10. Find the area of the mural in square inches. Well, if I sketch my first little picture here, right, this is 4.8 by 7.2. So I know that that area is going to be 34.5 0.56. All right. Now that's all the information we need here, because we know that area 2 is going to be equal to area 1 times the scale factor squared. So area that we're looking for is going to be equal to the 34.56 times our scale factor 10 squared. 10 squared we know is 100. So the area of the mural in square inches is going to be 3,456, and those are going to be inches squared. Okay? Now our last problem, right, a little bit more complicated but kind of a neat question. Logan's flying a kite that's made up of 3 similar rectangles. The sides of the 3 rectangles are in the ratio of 1 to 2 to 3. If the area of the smallest rectangle is 72 square inches, what are the areas of the other 2? Okay? Well, let's see. Once again, a little sketch to help me out here. So that's 1, right? That's going to be my 2. That's going to be my 3, right? My 3 rectangles. And we know that we're in a ratio of 1 to 2 to 3. The area of the smallest is 72. So I'm going to put a 72 here to just help me see it. Okay? So let's start with this question here. So we know that the area is going to be equal to, right, let's call it area 2, is equal to area 1 times the scale factor squared. So area 2 is going to be equal to area 1, which is 72. But what's the scale factor? Well, the scale factor here, if I'm going from 1 to 2, that's a scale factor of 2. So that's going to be 2 squared. 2 squared is 4. 72 times 4. So area 2 is going to be equal to 288. Those are square inches. So this is 288 square inches. But what about area 3? What's that going to look like? Well, area 3 is going to be equal to area 1 times the scale factor squared. Area 3 is going to be equal to area 1, which is 72, once again. But we have a different scale factor to go from here to here. Right? Look at the ratios. 1 to 3 means that we have a scale factor of 3, but we're going to square that. So what's my area 3? Well, 3 squared is 9. 72 times the 9, that's going to be 648. 648 square inches. All right, so just to review quickly, we have the several rules. The first rule we started with is that the ratio of the perimeter of similar figures is equivalent to the ratio of the corresponding sides, and then we had the ratio of the areas of similar figures is equal to the ratio of the squares of the corresponding sides. All right, I hope that that's been helpful, and we'll see you soon.